All right, not perfect, but hey, that's the life in it. This is Mr. McMurray. This is Physics 1417. If you thought you might be in the wrong place, in some kind of music appreciation course. I used to play music. I always like to play music the first of my videos, but when I upload them to YouTube, they get kind of picky about that. They begin to send me a nasty message saying I couldn't do that, and I don't know why because I downloaded the whole song off of YouTube, so I don't see why they won't let me use a little clip in my video. But who knows? I'm sure there's a way to sort that out, but I haven't figured it out yet. Anyhow, moving on. This is welcome to Physics 1417. This is the first video for chapter 15. We're going to talk about chemistry. There's not a whole lot of drastic chemistry that you probably haven't heard before in high school or other classes already before now, maybe even junior high. For tonight, not anything too extreme, but basically, hopefully you've had a chance to look at the internet and have seen that your class, either 502 or if you're dual credit 601, and clicked on those just real quickly. I don't spend a lot of time on it, but you should have a video that kind of explains how the web page works. There should be a place for a syllabus. Okay, there's one online. There's also where you can download one and print it off if you'd like to have a copy to see if Mr. McMurray sticks to what he actually said. Feel free to point out any typos. I almost always miss the year on a couple places and have the wrong year or something silly like that. If you haven't done your intro materials, well, yeah, we'll get to that in a minute. I guess we'll talk about that. But basically, it's very simple. If you click on, there's the chapters and articles, which we'll talk about, and exams, and you can click on this to get there. You can also go straight to modules over here, which will take you to module. But if you click on these, it'll take you to the specific chapter you want on the modules. Now, before chapter 15, there's actually some introductory stuff. An academic integrity policy, which basically means you say, I will not cheat. An online student statement, where I said, I will not break the internet. Leave that to Wreck-It Ralph, whatever. Okay, anyhow, click on those, you accept or say, I agree, whatever, and you get 5 points. And there's also one that says introductions. Now, Mr. McMurray had originally signed it for August 25th because he imported this from his class in the fall and he forgot to change the date. So don't forget to go back and do that one if you haven't already. Just enough to tell me a little bit about yourself and so forth. Okay, easy assignments there, and then you get to the more serious stuff. All right, in most chapters, you're going to have, I give you an outline of the notes. Okay, not the actual notes, not fill in the blank outline exactly, but just kind of a rough, yeah, here's kind of the things that are hit. Hopefully you can see that whether you've gotten most of those or not in your notes. And then there'll be a video of lectures, okay? And those will be cover pretty much the whole chapter, okay? There are some things that we'll cover in these lectures and demos. So every week I will post a lecture like this one that has lecture, kind of hits the high points, and it will do demos. But this one is not intended to replace watching all of those. Okay, good news is they're only 15 minutes long. One, because that's the only way you could do it on the free Screencast-O-Matic program that I used originally, but also it keeps you from falling asleep and trying to figure out where you left off before you fell asleep. So at least you only have 15 minutes to scan through to find it. All right. Now some of these have worksheets and stuff like that too, but most of them will have the notes, the videos, and review questions. And then there will be a quiz at the end of it. Okay, now to take the quiz, you will eventually need to do the lockdown browser, which is over here on the side. Okay, and if you click on that, it'll kind of take you through the steps and that will set it up. Just so that when you take the quiz or test, you can't go to any other web pages besides the quiz. Okay, so you'll need to install that. We will have the first quiz, coming up. Let me go back a little bit, sorry. First quiz will be coming up. There's one elementary quiz, which is just a practice quiz. Notice it's not worth any points. It's just there to test to make sure that you've kind of learned your elements and your symbols. But it's a good one also to practice on and see if your browser is working, that your browser is compatible with a lockdown browser, and it's going to work. Okay, and that way, by the time you get to an actual quiz that counts, which will be by the 23rd, which is next Monday, hopefully we've got all those any bugs in the system worked out and got your lockdown browser hooked up. All right, but that will be for quizzes and tests. Now there are some extra things on this one. I have a picture of a periodic table, so in case you don't have one, there should be one also in the back of your book. elementary ID. These are just a list of 27 elements and their symbols. You have to look up, I believe, the names. I think I just gave you the symbols, if I remember right. And you just need to be familiar with these. I'm not going to ask you specifically, but life will be a whole lot easier if you know what these elements and their symbols are. Okay, and there's also an atomic worksheet. This is just a chance to practice some problems. It should look something like this. It has where you put the electrons, protons, neutrons, that kind of thing, the charge, and then you draw pictures of them. Okay, just kind of making sure you understand the stuff we're talking about the basic atomic structure. Okay, it will not be for a grade. I will post the key to it on Sunday, as well as a key to the review questions, so that way you can check to see if you had the right answers. The review questions are mostly a completion grade. So, yes, you completed it. The question is, did you get the right answer? So it's always a good idea to check that if you're not sure about some of your answers before you take the quiz. All right, and then eventually there'll be tests and stuff like that. All right. All right, the book that you will need is Conceptual Physical Science. It's actually a pretty good book. It's certainly a readable book, and although it may not be readable since it's doing the mirror image thing on me. But Conceptual Physical Science Exploration should look something like this. Now, this one's a hardback. I didn't have a hardback. I had a paperback, and most people that get one get paperback, certainly cheaper. And so I would recommend getting a paperback, unless you can get this one for the same price. But one of my students found it in a hardback, and so when the course was over, they gave it to me, so I would have a hardback. Woohoo! But when you ask them for a teacher edition, they give you the cheap paperback. Okay, anyhow, point is, this is a book. It's fairly easy to read. It's actually fairly good for a book, a science book. Some science books are really difficult to actually use and learn from, but this one is good. We will cover some things that probably aren't in it, vice versa, not cover some things that are, but it is a good basic book. Now, train of thought, lost it. Okay. Yeah, if you're worried about you haven't got one yet, you will be able to. I have copies of the questions and so forth. And if you do a PDF copy, you can get the pictures that are in the book that go with it, and that will help you. But you do need to get the book. I would get one online. Usually, if you can get them used, much cheaper. I would not buy a new one. Okay, so definitely get one of those. All right. Okay. Now, moving on, let's talk about today's lecture. Okay. We are going to talk a little bit. Let's go back to my PowerPoint here a little bit. Some things to start off with. Okay. First of all, chemistry is one of those things we talked in the last semester. If you were here, and if you weren't, we still talked about it. But we talked about the importance of this differentiating between fake science and real science and stuff like that. And we like to think sometimes, I think we're superior to people who believed in snake oil and all these different superstitions that if you, what was it, in Tom Sawyer, you cut off a wart and buried it in the cemetery at midnight, you would get cured and things like this. But the fact is, there's still a lot of fake science out there. Why? Because it makes money primarily, and especially when it comes to health, beauty aid, things like that. Some things are just exaggerated. For example, kale is good for you. Is it going to make you live forever? No, there's a lot more things that affect you than just that, but it is healthy and it's good for you to eat it, just like all your green vegetables. Okay. And there's all kinds of things, supplements being sold, and they're not necessarily harmful, but the odds are most of those, if you're eating a decent diet, you're getting all of those already. Okay. And if you're not eating a very healthy diet, then eat a healthier diet. Okay. But there's billions of dollars of money going into that, in the industry of diet pills. I mean, every time I get my iPad and have to watch the ads because I'm too cheap to buy I just take the free version with the ads, of course. And so all the ads about how you can miraculously just take these gummies and you'll lose 70 pounds. Well, trust me, if all you had to do was eat gummies to lose 70 pounds, there wouldn't be any overweight people. Okay. And so there's still a lot of fakery out there. Okay. And one of the other things I want you to do is we're going to be talking about chemistry, first of all. We'll be also covering other things later on the year, but at least half of it or a little more is going to be about chemistry. And one of the most important thing is chemicals are not necessarily bad. Okay, and if you look at this little label here, I like this. It says Mother Nature is lucky her products don't need labels, and then it lists all the ingredients that are found in an orange. Now you can't see this because it's fairly small, but they're long, complicated names, dangerous sounding chemicals. Okay, but it's an orange and it's perfectly healthy and it's good for you. Okay, now this was made by the Monsanto company, who same people who brought you Agent Orange in Vietnam that killed lots of stuff and did a lot of bad birth defects and stuff to other people. Okay, now their argument is, well, all chemicals are natural. Well, okay. Some people think, oh, I'm not going to eat that because it has chemicals. If they look on the ingredient list and they see something that sounds like a chemical name, then they're going to say, I'm just not going to eat it. Well, first of all, they are right. Everything is made out of chemicals, no matter how natural it is, whatever. Okay, so don't be afraid of something just because it has chemicals or just because it has a big name. Okay, natural sounds good most of the time, but arsenic is natural. Okay, does it mean you should eat it? No. Okay, so just because something's natural doesn't mean it's safe. Just something a chemical, that's not good or bad. Everything's made out of chemicals in the world. Okay, but on the other hand, some chemicals are dangerous. Okay, I have a cartoon once that says it's it's foolish to be afraid of everything, but it's stupid not to be afraid of things that are dangerous. Okay, and so we kind of need to have some common sense about what is dangerous and what is not. Okay, if you eat carbs, you're not going to die. Okay, you're not necessarily going to be obese. It's a matter of how much you eat and how many you eat. Okay, and so when certain chemicals, corn syrup, for example, got a really bad rap. It's sugar basically. Okay, yeah, if you eat too much of it, it'll rot your teeth out and do whatever. But so will any other sugar. Okay, it's probably not that much worse than anything else. They haven't really come with any conclusive proof that your body uses it that much differently or whatever. Okay, so once again, be reasonable about these things. Don't just get on the latest fad of some superfood that's going to solve all your problems, or that some chemical proteins, carbohydrates, whatever, are bad. We should never eat them. Okay, basically, your body needs a balance of all of those. Okay. On the other hand, you can't just accept when, say, a chemical company says, "Oh, we're spraying this new chemical and it's great." Okay, it's good that we have agencies whose job is to make sure that those chemicals they spray are actually safe and don't cause problems. All right. Sometimes they mess up and dangerous chemicals are used. All right. But on the other hand, uh, there have been some sweeteners, for instance, saccharin. Sorry, I was going to say strychnine. Strychnine is dangerous. Saccharin that was linked to some things, and now they've kind of gone back and said, well, maybe it's not as dangerous as we thought it was. They're kind of back and forth on that. Caffeine is something that we've said there's good things about it, but there's also bad things about it. It speeds up your heart rate, does other things. So you kind of have to weigh. Most things are not just a simple cut and dried. But the idea of this class, hopefully, we'll get some common sense about chemistry and realize that just because something has a big chemical name, that doesn't mean it's necessarily good or bad. Okay, you just have to kind of find out more about it. All right. So enough of my soapbox. Let's move on. Basically, we're going to talk about atoms, first of all, how an atom is made, because everything in the world is made of atoms. But what is an atom? Do we even know if there are such things as atoms? Well, first of all, we have what we call models. Over time, we've come up with different models. And a model, just like a model airplane, is not the real thing. It looks like the real thing, and the better model it is, the more it is like the real thing. But it's not exactly the same as, okay? And we have never ever directly seen an atom and its parts. Everything we know is indirectly. All right, we have not actually seen it. All right, but if we have a model that explains how the atom works, and if it seems to fit with what we see happening, then we think that's a good model, especially if that model allows us to predict what will happen. All right, if that model allows us to predict what will happen, then it's probably more likely to be closer to the reality. So I can say that no, we do not know what an atom looks like, but the models that we've come up with fit the way they work, the way they react with each other. It fits these models, and as we've improved the models and based on what we've learned more and more about them, we think they're more accurate. But We don't know if that's actually what an atom looks like. Why? Because an atom is smaller than the wavelength of light, which means it will not let wave lights bounce off of it and look through it through a regular light microscope, no matter how strong or powerful it is. Now, we can use electron microscopes, electron scanning microscopes that shoot electron beams, electrons being a part of an atom, so they're very small, and we can get little fuzzy ball-like pictures, but it's still not exactly what an atom looks like. It's just showing us there are little ball-like things there that we think are atoms. Okay. Now, long before anyone even thought of being able to look at an atom, the idea of an atom came back way back when the Greek guys were running around in togas, and the guy who ended up being, we think, most right, and that there are atoms, was a man named Democritus, and his idea was not accepted for a long time, certainly not while he was alive. Okay, but his idea was that if we took a piece of something, we cut it down to smaller pieces, eventually we get to a piece that is so small you can't cut it into anything less without destroying it. Okay, and he called that the atomos, or indivisible. The cannot be divided. Not invisible, although it is so small, one atom would be invisible, but indivisible, like in the Pledge of Allegiance, one nation under God, indivisible. Okay, that kind of indivisible means it cannot be divided anymore. Now, technically, atoms we've found since then can be divided and give off lots of enormous energy when they do that. But most of the time, first of all, they do not divide. And when they are divided, they are no longer the same atom anymore. So, fitting that definition of something that's so small that if we split it, it won't be that substance anymore, he was basically right on that. That's what he thought. Now, Aristotle, another Greek, who we talk about now about how he was wrong about things, but he was one of the first scientists who kind of described things and explained how they work. So that's what happens when you're the first one. You're going to be wrong about things. But anyhow, he said everything is made out of different amounts of earth, wind, water, and fire. And by mixing them together in different amounts, you got all the different substances in the world. Okay. Now, he was on to something because he does have some very basic principles of chemistry. You have earth, which is solid, you have wind, which is gas, and you have water, which is a liquid. So he talked about the three phases of matter. So they are a basic characteristic of matter. It's just that that's not what they're made out of. We don't mix different amounts of solid liquids and gases to make things. Okay. And the other thing, fire, is energy, which is very important in chemistry also. So his ideas are important to chemistry and did eventually lead to the phases of matter and the idea of energy. But he was wrong about what things were made out of. We think Democritus is the most accurate. There was a man in about 1827, and Brown was his name, and he was looking at pollen grains on water, and he noticed that pollen grains were constantly bouncing around. Okay, but it wasn't until about 1900 that Einstein basically explained what we call Brownian motion. Okay, these small particles in a liquid, by the fact that the atoms are actually bouncing around and moving them, and Einstein really kind of proved this. Up until then, there were a lot of people, especially in physics, who didn't really believe that individual atoms still existed. That maybe it was just, that was really the first direct proof or explanation that proved that things were made out of atoms. Okay, we're so used to accepting that things are made out of atoms, that's not a big deal to us. Okay, but anyhow, basically, anything that is made of atoms, everything is made out of atoms. Anything that's made of one kind of atom is called an element. Now, if I look at a substance, okay, for example, if I have the cork, can you tell me if all the atoms in there are identical? Well, if you look at it very closely, you can see there's light parts, dark spots, stuff like that. So probably you could say, no, that is not all made out of the same kind of stuff. Okay. On the other hand, if I gave you this ball and said, hey, what's that made out of? Is it an element, just one kind of atom, or does it have more than one kind of atom? That would be a little harder to decide, okay, just by looking at it. Okay, this one looks very similar also. Okay, it's not quite as shiny, definitely not as heavy if you could feel the weight of it. All right, but this one is an element. This is aluminum. Every atom in it, mostly, is aluminum. On the other hand, this one is iron. Well, actually, this one's steel, which is iron plus carbon or other elements added to it, stuff like that. Okay. All right. Sorry, that bugged me when I was doing my glasses are crooked. Okay. Anyhow, so basically, this is not an element because it has more than one kind in it. Now, when we say something is made completely of one kind of atom, all right, can we really tell that every single atom of there is something? No, we can't. So, like gold is, to be pure gold, it has to be like 99.98% pure. Okay, that means like out of every 10,000 atoms, we would think there might be one, and that's pretty good. Okay, most of the time, we're probably not that high close to purity, but the idea of an element is things are only made of the same kind. All right. And atoms are mostly space. That seems really hard to believe because, well, how can something be solid or whatever and have shape and stuff and yet be mostly space? All right. Well, let's talk about it a little bit. All right. First of all, we have two parts of the atom. We have the center of the atom, and we have stuff that circles around the outside. Okay, the center of the atom are called, the things in the center of the atom are called nucleons because they're in the nucleus or the center of the atom. All right, this is not like a cell nucleus. That's a whole different thing. It has bunch of atoms in it, but each atom has a nucleus, and in that you have two things. You have protons, which have a positive charge, and you have neutrons that have a neutral charge, not negative, neutral. Okay, a lot of times people think in negative, but it's neutral. All right, so you have positives and you have neutrals. All right, they both have about the same mass. They're a little bit different, but they're about the same. Technically, a neutron is a little bit heavier than a proton. Okay, but they're pretty doggone close. Okay, but it's such a small amount that we don't use it grams or pounds or something like that. It's in, we made up a whole new unit called AMU, atomic mass unit. In other words, a unit to measure the mass of an atom, okay? So atomic mass unit, okay? An AMU. And technically, since they don't weigh the same, what they did is they averaged the weight of the two of them and said 1 AMU is equal to that average, halfway between them, okay? But for practical purposes, since it's like 0.000 grams difference between them, we just say they both weigh 1 AMU. But just for the record, neutrons weigh a little bit more than protons. Okay, but the one's positive, one's neutral. Those are in the nucleus. Now, protons are positive. If you have a bunch of positive charges together, what do? They attract each other or repel? No, they repel, and they go shooting all over the place, okay? So neutrons kind of get in between there and help hold them together so that you have a solid nucleus, okay? But the nucleus still has overall charge of positive by however many protons it has. The kind of atom is determined by the number of protons. If you look on your periodic table, element number 1 is hydrogen. So if something has 1 proton, it's hydrogen. Period. Doesn't matter. Okay. It will always be hydrogen. Why? Because it has 1 proton. Okay. The neutrons can vary anywhere from 0 up to 100 something. Okay. Usually in most atoms, there are either more neutrons, the same number of neutrons, or more neutrons than there are protons because their job is to hold all the protons together. And if you had more protons, then they would probably start repelling each other and bouncing all over the place. Okay. Now, so say we have an atom that has 1 proton. That's it. We know 1 proton, that's the atomic number, means that it is atom number 1 because the atomic number, the number 1 of hydrogen on the chart, tells how many protons it has. Okay, so it's 1. Now, if we add a neutron to that, it still has 1 proton, so it's still hydrogen. It's just a hydrogen with a little extra weight, double the weight, in fact, to be honest with you, okay, because it has a proton and a neutron, but it's still hydrogen. That would be called an isotope, okay? It still will act like hydrogen, can be used in our bodies or whatever, just like any other hydrogen, but it weighs a little bit more. And so these are called isotopes. They have different number of neutrons, okay? And so they have same number of protons, but different number of neutrons, so they're isotopes of the same atom. Now, the first one had 1 proton, so its mass would be 1. So it would be called hydrogen 1. Okay, so if you take the name of the element plus its mass, that helps you tell the isotopes apart. The second one had 1 proton and 1 neutron, so it has a mass of 2 AMUs. So we would say that is hydrogen 2. Okay, and so on. And technically, if you had 2 neutrons, 1 proton and 2 neutrons, then it could be hydrogen 3. Okay, so that's one way to refer to them. All right, so they could also be referred to as if you had H and then Woo, Douglas. Okay, if you had the H, and then over here you would put the mass number on top, like 1, 2, or 3, depending how much mass it had, and the proton at the bottom. I think I went over that in the other lecture, but just to kind of cover that. Um, so that would indicate, that's how we indicate different isotopes, so we know which ones we're talking about. More about that when we get to nuclear energy. All right. Um, Now, what does that leave us with? Well, we have the nucleus, the nucleons, the particles that are in the nucleus, the protons and neutrons. Around that, circling it, we have electrons. Electrons are very, very, very small. Compared to a proton, they're like 100, less than 1/200th of it. Okay, there would be point if a neutron or proton is 1, a electron would be 0.0009 something, almost 1/10,000th as much. Okay, very, very small compared to that. In fact, when we're adding the mass of the whole atom, we don't even worry about the electrons because they're so small. So if we want to know how much the atom weighs, we say, well, how many protons does it got? How many neutrons does it have? Okay, and then we add those together to get the mass. The electrons are so small they don't really matter. But they have a charge, a -1, and their negative charge is just as strong as the proton's positive charge. Okay, and so even though they're tiny, they're still just equally important. Now, if you look on a periodic table, there we go, get that up, you will notice the number like here for hydrogen isn't 1, which is the most common, 1 um, proton all by itself. In fact, the vast majority of hydrogen atoms only have 1 proton and no neutrons. All right, so they're hydrogen 1. But you notice the number is not 1, it's 1.0079. So it says, oh, well, that's because the electrons. No, remember the electrons still weigh 0.000, way down here. They just hardly weigh anything. They wouldn't weigh enough to make that 0.0079. So it would take like 79 of them or so to make that much. So where does that come from? Well, since they're not all the same, they don't all weigh 1, this is actually the average. Okay, it's almost 1, 1.0079. So that tells us most hydrogen atoms weigh 1. But there's some that have 2 or 3 as their atomic mass. And so when you average them all together, you get a lot. You get a slightly bigger number, bigger than 1. Most of them would have a mass of 1. So now I know you're wondering, how can I figure out how to get that average? Well, let's just say carbon. Okay, most carbon in the world is what we call carbon-12, which means it has 6 protons and 6 neutrons. And about 99% of all atoms in the world are equal to that. Hey, hang on. I flipped the camera so everything's going to be backwards. I apologize for that. But 90% of carbon-12. So that means about 1% of it is one called carbon-13. Okay, there's also carbon-14, it's even smaller amount, but we're not going to worry about it. We're just going to round it off. Okay, so if I took 99 or 0.99, which is what 99% would be, times 12, which is what one atom of that carbon weighs, and I take 0.01 times 13, which is what the 1% of atoms that weigh carbon-13, then I would get a number up here, and if I add them together, I would get what it says on the paper, which I think is about 12.001. Is that right? I forget, but you can do that and calculate it and add it up yourself. But that's what you do. If you know the percentage of each isotope, multiply that percentage, well, change it to a decimal, whatever, and multiply it times that, and then change this to a decimal, multiply it times the mass of the other, and then add them together, and that will tell you get that average that they have. Okay. All right. Now, electrons, we were talking, you got these electrons. Um, electrons, you have the protons and the neutrons in the middle, and then these electrons circle around the edges. Electrons are negative, all right? Why do they not go flying off? Because they're attracted to the positive protons in the middle, okay? They want to be so close to you. Okay, there's a carbon or something like that. Anyway, they want to be close, okay? So they are pulled or attracted by that. There are different levels. If they get more energy, they can move out to farther levels. All right. The first level can hold 1 electron, 2 electrons, and then it's full. Okay. The next one can hold up to 8. Okay. The next one can eventually hold up to 18. We'll talk about that later. And then the next one Can eventually hold 18, and eventually get to ones that can hold 32. Okay. Well, actually, I take that back. Yeah, we won't worry about that. Okay. We're not gonna worry too much about that for now. Just know there's different levels for now. We'll get into the GUI details later, how that works. Okay. And they can have up to the biggest atoms we know of 1, 2, 3, 4, 5, 6, 7. You can have up to 7 different layers, okay, or shells. We call them shells because like the layers around it. Uh, we also call them orbitals because they orbit around it, and because sometimes they can jump up, they gain energy, they can jump up to the next level. We call that energy level. So you may come call any of those orbitals, energy level, shells. It's all the same thing. All right. But if you look at the periodic table, you will notice, guess what? There are 1, 2, 3, 4, 5, 6, 7 levels. Someone says, well, technically, what about these two down here? Aren't there 9? No. These 2 rows at the bottom should be right here. But as you can see, when you put them there, that shrinks everything down to make it fit on a piece of notebook paper. So scientists said, let's just cut these 2 rows out, put them down here on the bottom, and then everything's big enough so you can see what it looks like. And that's literally what they did. If you look at the numbers, they match. You go 56, 57, all the way down here to 71, and then you go back up here to 72, and so forth. Okay, and this row here matches right up there. So you have 7 levels of electrons. You've got 7 rows or periods. They're called periods. The rows are called periods on the periodic table. Boom, there you go. And so guess what? The first periodic table the first level has 2 electrons. That's why the first level has 2. There are how many elements on the second period? 1, 2, 3, 4, 5, 6, 7, 8. That's why the second layer has 8. Okay. The third layer has 8. The fourth layer, and this is where it gets complicated, has 2 here and 6 here, which makes 8. But then they start, before they get to these last 6, they start filling up the third level with these. Okay, it gets kind of complicated. We won't worry about that. But notice that each layer on the atom of the electrons corresponds to these periods. Okay, now periods, that's why it's called the periodic table, because as you go across the periods, the elements change. Okay, we call these periodic trends. In other words, what do they tend to do as you go across? They change, but they change in specific ways. Okay, very consistent ways. All right. The columns are called groups, or in some instances, they're called families, and they are very not like each other. I mean, they are, excuse me, I just said that wrong. They are very much like each other. The periods are not the same because they change as you go across, but the groups are pretty much all the ones in the same column have things in common. There's a few columns we'll talk about later that are exceptions to that, but for the most part, the groups, the families, the columns are similar to each other. They have, and that's why it's called periodic, because as you go across the period, you go all the way over here, and then boom, you come back and you have a repeating pattern. Okay, and so if you put them in this repeating pattern, all the ones that are like each other line up in the same column, and that's where they eventually came up with the periodic table. All right. Now, elements in general in nature can be different shapes, sizes, and stuff. All right. We have some that are fairly common. For example, sulfur, which is what makes matches stink, among other things, are kind of a yellowish color there. It has a little bit of an odor to it. A lot of times you'll see it as a powder crushed up into a powder. If you burn it, it will smell awful. Okay, so that has a very strong smell. Sulfur and associated brimstone and stuff like that. Carbon, basically charcoal, basically is carbon, pure carbon black. Well, I don't say carbon copies. Used to be pages that had black stuff on one side that came off when you typed on it or whatever. Okay. Yes, back in the old days, that's right. We did those things. Um, and so forth. So you have all these different elements. Some are solids, some are liquids. Okay. Some are gases. Most of them are gases. I don't know if you can see this very good. This is a you can kind of see it there, I guess. Okay, well, let's see. Ooh, you see it going back and forth, maybe. All right, that is some mercury. All right, we got some mercury metal in there. It's actually a liquid, which is very uncommon. relatively uncommon. There's only a couple of elements that are liquids on the chart. Bromine is another one that is. There are some, though, like here is gallium. And if I were to let this one sit in my hand, I have a little bead of it there. I'm not going to hold on to it too long, because if I hold this long enough, it will start melting at body temperature. Okay, so it's just barely a solid. Okay, a lot of the other ones are gases, especially when we talk about non-metals like oxygen that we breathe, carbon dioxide we breathe out, all those kind of things. So there are a lot of, mostly they're solids and gases, and some uh, liquid, just a couple of liquids. All right. And it's hard to believe all the millions of things in the world that are made of all this different stuff are only made out of that. Really 90 elements. There's 118 altogether, but a lot of the last ones are ones that only exist in laboratories for short period of times. They've been created in a laboratory, they've existed, but for very short periods of time. Some of them just seconds, if that. Okay, others may last a little bit longer, but they fall apart and they can only be man-made. They don't exist in nature. Only about 90 of them occur in nature. And to think that everything in the world is made out of just those 90 things is really pretty incredible. Um, now, uh, in general, you don't find pure elements. When I show you a piece of pure aluminum or the mercury that's in here, okay, to find a pure element, we have to work at it to purify it to get it to that stage. Generally, elements are going to be combined with other elements. The exception to that are some gases. Oxygen is fairly common in the air. Nitrogen is the most common. 78, almost 80% of our air is nitrogen. About 18, not, a little less than 20% is oxygen. Carbon dioxide, water vapor. Well, water vapor is not an element. Sorry, carbon dioxide is not an element. Say there, those are got. But hydrogen is fairly common. Helium gas, some other gases exist, but as pure elements. But in general, most elements have combined with other elements. Otherwise, we'd only have 90 things in the whole world, right? And that would be very boring. So, yeah. Let's do one last thing before we stop here. We talked about trends. We said as you go across the period, things change in trends. Let's talk about a trend there. If you think about the radius, well, as we know, as you if you go from element number one that has atomic number one, that's one proton. Helium has two protons. So, the question is helium bigger or smaller than hydrogen? Well, it's got to be bigger. Well, it does way more because it has more protons. Okay, but there's something else that's happened. How many layers of electrons does it have? One, because it's on the first row, right? They're both on the first row, so they have one thing. And hydrogen only has one proton to pull that electron in. But helium, it has more electrons, but they're still on that second row. They're still in that first row, and now you have two protons, so it can pull it in tighter. Because as you go across, even though they get more massive, they have the same level or number of orbitals of electrons around them, and so they're on that same level, and now there's more positive charges, more protons pulling them in, so you actually see a trend where they get smaller. Let me see if I can find the chart. And generally speaking, you will see that as you start on this side, these are the biggest ones because why? They've just got a new row of electrons compared to the row above it. But as you go across, that shell, whichever it is, first, second, third, fourth, fifth, sixth, seventh, all right, gets sucked in closer and closer because there's more protons in the middle pulling it down. Now, there are a few exceptions, and we're not going to go into why those are exceptions, but basically, you see that same trend all the way throughout. That as you go across the periodic the radius of the atom, how far across it is, gets smaller and smaller because you're getting more protons, and they're pulling those orbitals of electrons in closer. So the whole atom gets more massive, but it takes up less space, okay, or has a smaller radii, okay? And there's some other trends that we'll talk about as we get into it, but electronegativity and some other things, but there we go. All right, now, does it, just for the fun at the end, Does the periodic table have to look like it does? No, some people have suggested some really weird shapes, and there's some good reasons for that, and there's some bad reasons for that. But for the most part, everybody seems pretty much satisfied with this one, and that's pretty much what you see, give or take a little bit. Some have more information on them, some have less information on it. Now, the good news is a periodic table, some people panic when they see a periodic table, bad memories from chemistry, but basically, the periodic table is an open book. So if you get to use it on their test, it's like you have an open book test. Why? Because all the information is there. Part of what we'll be doing this semester is learning to read the information and figuring out what it means so that we can see it and it will be an open book to us. All right. Okay. Don't forget to do your introductions. Don't forget to do your review questions. They'll be due by Saturday night at midnight. And then next week, um, we will take the quiz over chapter 15. Have a great week.